Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 109. It's on wave interference. In other words, what happens to waves when they hit objects or hit other waves? All the animals pictured here use echolocation. What does that mean? They generate sound waves that reflect off objects, and when they come back, they can figure out what they're looking at. Now, waves will also hit other waves, and as they do, sometimes the overall wave becomes larger, and sometimes it becomes smaller. So let me give you an example of that. I've got a slinky here, and I'm going to send two waves towards each other. Watch what happens when they meet, so the wave becomes bigger. But did the waves bounce off each other, or did they move through one another? Well, it's kind of hard to tell. Since both waves are on the same side, we don't know if they bounced back or if they went through. So a better way to figure this out is to send waves on either side. So I'm going to send a wave from the left on the top and from the right on the bottom. You can see they interact, but now the wave on the bottom continues to the left. And so when waves hit, they interact, but they move through each other. They're not reflected off of each other. And so wave interactions can take place when a wave interacts with an object, hits an object, or hits another wave. So when that interaction is with another object, we get reflection. It bounces back. Now, it depends on what we're hitting as to how we bounce back. And so if it's a fixed object, the wave, for example, the slinky hits something that doesn't move, it'll actually be inverted when it comes back. In other words, the wave goes in this direction, it's on the top, and when it comes back, it's going to be on the bottom. That's only if it's a fixed object. What happens if it's a free object? Well, the opposite happens. And so as it comes in now, let's say that this is able to move back and forth. The wave comes in on the top and it goes back on the top. And so that's reflection. Now when waves hit each other, we get what's called interference. Two waves interacting. That interference can either be constructive. Constructive is when two waves comes towards each other and they're both on the top. So what do we get? When they hit, we get one big wave. We're adding those waves together. So we're constructing a bigger wave. If it's destructive, we're on either side, and what do we get? We cancel each other out. So we are destroying the size of that wave. And so we use the law of superposition to figure out how big that wave is. And it's really easy. If you're 1 centimeter on top on both of those waves and it's constructive, we just add 1 plus 1 and we get 2. And so as waves bounce back and forth, what we can do is we can build up what are called standing waves. Waves that appear to not move, but what they really are is the addition of the waves bouncing back and forth. And so let's look at this using a PHET simulation. Let's start with a fixed end. So remember, if it goes into a fixed end, watch what happens. As it comes back, it's inverted. So it went down on the top and it came back on the bottom. Watch what happens if we now change that from a wave interaction where we have a free end. So it has the ability to move up and down. It comes back on the same side. And so again, it depends on what we're hitting as to how we come back, but we are coming back. We are being reflected. Now let's move into interactions between waves, when waves hit waves. And so that can be, remember, constructive or it can be destructive. And so let's start a wave moving down. So let me pause it for a second. Do you remember what's going to happen? We're hitting a free end. And so what's going to happen to that wave when it comes back? You should have said it's on the same side. And so let's do that. We were right. But you can see that I also generated a wave that's now moving from the left. These are about to hit each other. And so what's going to happen as they interact? Well, we should see constructive interference. And let's watch what happens. So we get one big wave right when they come together. Now what's going to happen to the wave on the left? Well, it's hitting a fixed object, so it should be inverted, and the one on the right should hit an object that's free, and so it shouldn't be inverted. So now what's going to happen when they hit? Should have figured this out. This is destructive interference now. And so watch what happens when they hit. They should cancel each other out. And we can just see this reflection and interference and reflection again. Example of this, I'm going to take a slinky and really send a pretty big wave. We'll do this in slow motion. You can see I kind of almost knocked my camera over. So the wave is moving to the left. It hits a fixed object and it was inverted. It hit my hand, which is a fixed object, and then it's going back in the other direction. So that's going to be that reflection of the wave. Now what will happen is if those waves keep bouncing back and forth and back and forth and back and forth, they're adding to and subtracting from each other, and so you get what are called these standing waves. And this is a SimBucket simulation. So you can see the green wave just appears to stand there. It's not moving. But what's really happening is that we have waves moving back and forth. So we have a blue wave that's moving to the right. It's reflecting back, and then it's moving to the left as this orange wave. And so as they move, they are interfering with each other. And so let's just grab one section right here. So why is this low? It's because they each are moving down from equilibrium, and so we just add those two values up. Why is the green right here at the middle? It's because we're above and below, and so we have destructive interference here, but we'd have constructive interference right here. In other words, we're building up that wave. Now we take advantage of that, so we can put sound waves that fit into a specific set length, for example, a pipe in a pipe organ, and you create what are called these harmonics of standing waves. And we'll talk about more of those in future videos. And so did you learn to make claims about what happens when waves overlap? Remember, they go through each other, but they can interfere. And then finally, could you look at a representation and figure out points when they're adding and when they're subtracting from each other? I hope so, and I hope that was helpful.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle's a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump rope. Now, I can find all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 1/2. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, Let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations. Let's derive the formula for the frequency of standing waves with this situation. It's a string that's attached at both ends. Since it's attached at both ends, these are both nodes. A node is a placement of no movement. You have complete destructive interference. Now remember what's really going on here, and refer back to the demonstration video to see it with your own eyes. But a wave is coming this way, it reflects, and then it constructively interferes with the next wave coming out in the middle. Here, wave comes this way, comes back, and with the new waves coming in, it constructively interferes here, constructively interferes here, destructively interferes here. This guy down here, he has an additional node there, plus these two, so a total of 3 nodes. This guy has 2 nodes in the middle and 2 on the ends, so 4 nodes. Now, let's derive the equation for frequency. Let's start with the wave equation. The wave equation, the speed of the wave along the string equals the wavelength times the frequency. Well, first thing to do is to measure this distance. Well, a full wavelength goes like this. So a full wavelength would be this. The length of the string is obviously just this distance. Therefore, we can see that this is half a wavelength, and therefore a full wavelength, lambda, I'll put it here on the side, is equal to 2L. So for the first possibility here, which we'll call the first harmonic, it's also called the fundamental frequency. We know that the wavelength is equal to 2 times the length of the string for the first harmonic. Therefore, rearranging the wave equation so that the frequency is the speed over wavelength, and then plugging in here, I'll call this F1 for the first harmonic. This equals V over 2L. Great, we got the first one. So that's this guy. Let's attack this guy now. Well, we can see that the wavelength extends from here to there. So we have up, down, that's one wavelength. So here, the wavelength equals the length of the string. So, very simple. For the second one, frequency is the speed over the wavelength, and since the wavelength is also equal to the length of the string, we just have this. Now let's look at the third possibility. Well, third possibility, we have one wavelength and a half. So here, 3/2 of a wavelength is equal to L, the length of the string. Therefore, one wavelength is 2/3 of the length, and that makes sense. This is 2/3 of the way to the other side. So, plugging in to the wave equation, frequency equals speed over wavelength, I have F3 is equal to V over, well, it's 2/3 L, and that equals 3V over 2L. I think we see a pattern forming. If we put a 2 here and a 2 there, we see that we get the frequency is of the form Fn equals Nv over 2L, where N is the number of the harmonic, and so, for example, we want to find the frequency of the 10th harmonic. Well, we would just plug in 10 here, and so for the 10th harmonic, we would just get F10 equals 10V over 2L. Plug in the speed of the wave along the string, plug in the length of the string, and you know the frequency of the 10th harmonic. So there you go. That's the formula for a string attached at both ends.